Hi everyone. Isn't this amazing? This PowerPoint theme. I specifically chose this one. I thought it was such a good representation of equilibrium. Ooh, and then it goes back and it starts again. Yeah, I'm like oddly too excited about PowerPoints lately. Anyways, okay, we are going to do, this is lesson 4.5. So lesson 4.5, interpreting concentration versus time graphs. So we already did the lab on this, so you already wrote that or drew that graph, I think. Sorry here. But now we're gonna really dig this apart and show what these things all mean. So this is our concentration versus time graph. Oh shoot, I meant to actually give this to people in person today and I forgot. My apologies. Anyways, so this is our graph here, or sorry, our graph here. So time is on the x-axis, concentration is on the y-axis, and we've got our three different species. So this represents a chemical reaction here. So first question here is to write a balanced equation to represent this reaction. So you can figure out what the reaction is just based on this graph here. So first of all, we're gonna, we look at a general formula for an equation and its reactants, goes to products, right? So reactants, we have to start out with some. So initially we're going to have reactants, but we don't have any products. So if we look at our graph here, the concentration of the COCl2 is 0, whereas I've got concentrations of the Cl2 and CO. So this tells me then that my formula is going to be CO plus Cl2, and then the COCl2 here starts at 0 and then starts increasing. So that's going to be my product. So that is my balanced equation here, and you just want to make sure you look at it and make sure that it's balanced, and it is, so we're all good. So that is going to be the balanced equation for this equation. For this graph, so this reaction, sorry. So we're just going to go through the series of questions here. So next, how much time was required for the system to reach equilibrium the first time and then the second time? So if we remember, we talked about this right at the beginning of this unit, and we talked about how equilibrium is represented when there's a plateau on the graph. So our first plateau is going to be here, right? So if I drop perpendicular down here, it's right around, I'm going to say 25 seconds. So the first one is 25 seconds, and then we're going to find our second plateau here. So the second plateau, of course, is right here, and so again I'm going to drop a perpendicular down, and it looks to be about 85 seconds. So those are our two first equilibriums. Now they don't end there. We've got another equilibrium here and another one here, but I didn't ask you about those ones. So anytime you see a plateau on your graph, so that would be when the concentrations are no longer changing, because that's the definition of equilibrium, right? The forward reaction is equal to the reverse reaction, so we don't notice anything happening. So equilibrium is going to be when those concentrations are constant, when they stop changing. Now, next one here, it says calculate the approximate value of the equilibrium constant from the concentrations at 50 seconds. So I'm going to look here. So 50 seconds, if I go up, so that's these concentrations. So I'm going to read them off the graph. Sorry, it's really hard to write with the stylus here. Now, it says to calculate the equilibrium constant, so that's from our last unit, right? So that, this is our KQ, where we've got products over reactants, right? So the products, if we look, if we remember, our product is our COCl2, which is phosgene, and we're going to divide that by our two reactants here. Now I don't have any exponents because the molar ratios are all 1-to-1 here. So basically I'm just going to plug in my values for this. So COCl2, if I look there, it's at about 0.0065, I believe, yeah. 0.65 molar, and then we're going to divide that by the carbon monoxide and the dichlorine there, the chlorine gas. So if we look at the carbon monoxide, we are at 0.151617185. I'm going to say 0.185. And then, sorry, is not right. I missed a 0. Okay, I'm trying to try that one again. The carbon monoxide is 0.0185. That's better. And then I'm going to look at the chlorine too, and that's going to be 0.00. And then that looks to be about 5675. Okay, so you just read those off the graph and then you just plug them into your calculator and solve, right? So it's going to be 0.0065 divided by 0.0185 and divide by 0.0075. And you get an answer of KAQ is going to be equal to 46.85. And I'm not going to worry about sig figs here because it's hard to get off the graph here. So 46.85, just remember that there's no units for that, okay? So my equilibrium constant, 46.85. Okay, now I'm asking you to calculate the value of the KAQ at 100 seconds. So now I'm going to look up from 100 seconds here. So this is this plateau. So I'm going to read them off. And here. So now again, I've got the same formula, right? So it's still going to be COCl2, so products over reactants. And now you're just going to sub in your value. So the COCl2, if I look there, that's going to be at about 0.00. I think that's kind of right around, let's say 82. Divided by, and now I look at the carbon monoxide, which is up here, and that's going to be 0.0, let's make it 17, and then multiplied by the chlorine gas, which is going to be 0.01, let's see, 101112. There we go. Okay, now we work that out. So 0.0082 divided by 0.017 divided, oops, shoot, 0.0, sorry, I gotta start that again, divided by 0.017 divided by 0.012, and I get the number 40.196. So that's my KAQ. Now, next question is, how do the two values of KAQ compare? So I've got 40.1 and I've got 46. Now, if I wasn't working with a stylus on an iPad here, these numbers would be closer together because in theory, they should be very close to equal. So the two KQ values at the different equilibriums should be close to equal, because remember, as you know, as the product concentration is increasing, the reactant concentration is decreasing, and vice versa. So that equality tends to be maintained, or the ratio is maintained between products to reactants. So normally the KQs would be very close to being equal. You'll see slight differences. I had a little bit too much. Like I said, I think it's just because of reading the graph properly there. Now, this is true except for when the change, or when the stress is temperature. When the stress is temperature, that changes things, because we know that increasing the temperature is going to increase both rates of the reaction. So if it's just the addition of a certain substance or volume issues, the KAQs will be this very similar, but when the stress is temperature, they'll change more. Okay, so what was the stress? You also need to be able to look at these graphs and identify what the stress is. So what is the stress that occurred at 70 seconds? So if we look, that's here. So that is the stress. So at 70 seconds, you would need to identify that there was the addition of, so what was added there? Cl2. So our chlorine gas, so extra chlorine gas was added. That's why we saw that spike right at that point. And those of you who did the lab with the straws, that would be when you added the 5 milliliters of water, 2.5, whatever it was, you would see that spike happen there. So at 320 seconds, what was the stress? So at 320, we're looking at this one. And so this one, again, we get a big giant jump. So this would be the addition of our COCl2. Now at 120 seconds is our next question, because here we also saw a change happening in equilibrium. So for this one, at the 120 seconds, we don't see a big spike either up or down. So we don't see the removal of a substance, and we don't see the addition of a substance, but we just see that there's clearly a disruption to the equilibrium and something's going on there. So in that case, it's either going to be, well, let's think about it there. It's would it be a volume issue? Because the volume, remember we go, so if we go, reactants to products, there was 2 molecules over here to 1. So say the volume was increased. So if the volume was increased, that means the reactants would increase, but that is not what happened on here, because we see our reactants decrease. So one possible thing that could happen there, you could say that volume was decreased. That would be a possibility. And we know that because the concentrations of the reactants decreased while the product increased. So we could say that volume was decreased, or conversely, we could also say that pressure was increased, because remember, P and V are inversely related. So there's different things, and we don't know what it was. We're just putting a guess together for that, okay? So volume was decreased could be the answer there. Now, looking at this one, how would the addition of a positive catalyst change the shape of the graph? So for this one, we know that the catalyst is not going to cause shifts in equilibrium, but adding a catalyst will make it go faster, right? So basically, this will be shorter on the x-axis. So shorter on the x-axis there. Good. Now, next one. So here we've got our reaction, so we can look at this and we've got the energy there, right? So we can say, okay, the forward reaction is exothermic. The reverse reaction would be endothermic. So list the changes you might impose on this system if you wanted to produce a maximum amount of phosgene. So if you want to produce a whole lot of phosgene, that means you want equilibrium to shift to the right. So how could you shift equilibrium to the right? So what about temperature? So temperature, if we added heat to this, that would actually drive equilibrium to the left, because it would favor the reverse reaction, because the reverse reaction is endothermic. So we don't want that to happen. So if we lowered the temperature,
would Mr. or Mrs. Starks please come to the Maples office?
So if we lowered the temperature, that would mean that the phosgene would be favored. So you would produce more phosgene here. Same thing you could do with volume. You could change the volume or the pressure. So if we, like we said, there's 2 molecules here, there's 1 here. So if we decrease the volume, we're going to drive equilibrium to the right. That would also help. We could also increase the concentration of CO. That would cause equilibrium to shift to the right, and we could also increase the concentration of chlorine gas, and that would also shift equilibrium to the right. So those are all things that we could do. I guess pressure I should list here too. If volume is decreased, that means that I could increase pressure. So all of these things here, these things are all going to increase the concentration of the phosgene, the COCl2. So we get quite a bit of information we can infer by looking at these graphs. It gives us quite a bit of information. Now, I don't have an assignment for this, but I want you to go through the interpreting graphs handout. It's a fair bit, so I want you to go through it and just really make sure that you understand what all those graphs are saying and what they mean, and it sort of takes you through all the different scenarios there. Okay, thanks everyone.